Thanks very much, Jamie. This is very self-indulgent, so this audience may well diminish as we go along if you cannot stand any more of it, and please feel free to express yourself in that way. So what I want to discuss is what I think should be classed as a major discovery in the 20th century, but invariably is not. This is Richard Ellis's list of the great surprise discoveries of the 20th century. Cosmic expansion, the hot Big Bang, dark matter, and cosmic acceleration. I don't think we could really disagree with any of those, but we might argue that a whole bunch of things have been missed, like other wavelengths. Richard Ellis is basically optical. The discovery that there were other wavelengths and the various objects that popped up, like the galactic center and AGNs and pulsars. Well, that, of course, is traditional radio frequency stuff. But nevertheless, I think there's a case for every one of these to be considered. But one which never really gets mentioned is missed from every list is the discovery that objects in the universe undergo dramatic cosmic evolution in either luminosity or density or both. And this discovery, in quotes, was made in 1955 to 1960, say, approximately, although it took about 40 years for it to really take. So I want to introduce the first of my protagonists then, as the person who really did make this discovery. Martin Ryle was a radar pioneer, worked on radar during the Second World War. In 1946, he and von Berg carried out the first interferometric radio astronomy. He carried out the first sky surveys, invented aperture synthesis, did deep synthesis map at the North Celestial Pole with Neville, whom some of you may know of as Anne Gower of UVic. Numerous awards and prizes, including the Nobel Prize shared with Tony Hewish for his part was aperture synthesis. Tony's was the pulsar bit. So sorry, this is a little bit dense. What was this discovery? Let me just pick out the highlights. Ryle's, which lecture was it? Not the Beckerian lecture, the Halley lecture in 1955. This was a traditional way in those days of announcing big discoveries. And this is the gist of Ryle's 1955 Halley lecture. That there is an apparent increase in spatial density or absolute luminosity of distant radio sources. This increase is independent of direction. It looks like the sun is situated in the center of a huge spherical region. It's impossible to explain the results by irregular clustering and impossible to explain them by a uniformly filled universe such as the steady-state universe. The minimum radius of this spherical region must be comparable with that of the optically observable universe. That's 1955 jargon, which means redshifts of 0.3 of order. Ryle suggests that the observed features are due to effects on a cosmical scale. There seems every reason to suppose that they might be explained in terms of an evolutionary theory. These are rare objects, very low spatial density, and on this interpretation, the difficulty of identifying what were then known as radio stars, the difficulty of identifying radio stars with optical objects has a natural explanation. Only a few of them would be within the reach of the Palomar 200-inch telescope. Well, we know nowadays that reach has extended out to redshifts of 5 and 6, but Ryle was discussing a reach of a redshift of, say, 0.4. So this beautiful paper, this groundbreaking paper, and then the real sums were done by Ryle and Peter Scheuer. What's the citation index look like for this groundbreaking paper? Here it is. There are a total of 5 citations, 3 of them in refereed publications. What about the proper paper, not the lecture, but Ryle and Scheuer? What did that throw up? Total of 16 citations. That's not the hallmark of a great discovery, I think you will agree. So what was wrong? Why was this not accepted? Well, here's why. The paper was based on this source count. And a source count, I don't think I need to explain to you, is the simplest curve you can get out of a survey. It is the number of sources per unit area as a function of intensity. Naturally, there are many more faint sources than bright ones. Again, naturally, a uniformly filled universe will have a slope of -3/2, which you can work out while I talk on the back of an envelope, the cube coming from volume and the 1/r² coming from the luminosity fall-off. So what you would expect in a uniformly filled universe is a slope of -1.5, -3/2. What Ryle and co-workers found with this 2C survey was a slope of about -2.7, which statistically is pretty incompatible with -1.5. And this is the basis, the real basis of Ryle's claim. What could possibly go wrong? Everything. Of the 1,906 sources in the 2C survey catalog, the majority would prove to be phonies, absolutely false sources. And why is that? Oops. Oh, no. Come on. Why is that? There are 2 reasons: Eddington bias and confusion. So I'm going to tell you a little bit about each of those things, each of those source count wreckers. But to do so, I have to introduce my second protagonist, Arthur Eddington. Eddington, in his time, was possibly the most famous astronomer, certainly in the UK. He was, as we know, an astrophysicist. He was an astronomer. He led the 1919 eclipse of Venus to show that Einstein's prediction was correct. He did a lot of work on general relativity. He was a mathematician, and making him best known to the general public, he was a brilliant expositor of GR at every level, and the British public knew him very well indeed. So what's his role in this? Don't read this.
Okay.
Don't read this. This is the full extent of the paper in 1913, Monthly Notices by Eddington, on a formula for correcting statistics for the effects of a known error of observation. And what Eddington showed is if you have a number-magnitude relation, which is optical jargon for a source count, and you have random errors on the measurements of your fluxes or magnitudes, then you will get a steepening of that count towards the fainter end will result. And it's the steepening of this count, which is known as the Eddington bias. The term is, in fact, used generally incorrectly these days to say that it's something to do with the measured flux density having the bias. But the original paper is clearly written to state that the bias is on the source count or the number magnitude relation and not on the flux itself. So here's the citations for Eddington, unfortunately starting only at 1954. We cannot guess what impact it had in 1913. Well, we can guess, actually. Pretty well not much. But here is what has happened to Eddington's little one-page paper, which he probably did in an evening or at a railway station. Here is what the citation index looks like, and that's because it's been discovered, particularly been discovered by the submillimeter galaxy people who now, since they're groveling around in the noise, now systematically correct their fluxes.
Those statistics for the Eddington effect?
No, I regret to say I haven't. Yeah. No, I haven't corrected this number count, I have to confess. But the trend is clear enough. It's cited frequently. I've even done it myself. What actually happens? Well, here is a Monte Carlo simulation which I carried out. Here is a source count in differential form this time, not the integral form that the counts were originally done in, that Ryle and co-workers used. This has a slope of minus 2.5, which is what you get for a uniformly filled universe. It's the counterpart of the integral slope of minus 1.5. And this is what happens when you have a scatter in the fluxes of some 5 units. And here is my flux scale here. So you can see that obviously when you get down to 10 units in your counting, Gaussian error of 5 units is going to be pretty serious. But it's much worse than people think. People laughingly pick off stuff at 3 sigma and think they're getting decent survey statistics. It's quite, this is a plot of the integrand of this thing, the curve convolved with the probability distribution of the errors. And it's quite clear that when you get to 3 sigma noise, say at the bottom of your survey, that you have no idea whatsoever of the flux, of the true flux of that source. There's no point in even thinking about correcting it. You don't know what's happening to it. At 4 sigma, you're not a lot better off. The bias is severe so that surveys which think they're comfortably above the danger area and count down to 4 times the standard noise are in for a terrible shock when they come to measure the sources properly somewhat later. Even at 5 and 8 sigma, you can still see that the fluxes that you measure, the sources that you get, are severely biased to weak sources. This is, and the effect is simple because simply described by if you have a weak source and you have and it's selected from a steep source count. If you have noise fluctuations, you are much more likely to include in your count weak sources, because the count is steep. You're much more likely to include weak sources with a positive noise boost than you are to include strong sources with a negative boost, a negative noise error. And that is the source of the so-called Eddington bias. That, in fact, biased the counts like anything. But it was far from Ryle's least concern. Ryle and company should have been warned by the simple shape of this integral count leveling off. I mean, a leveling off of an integral count is a clear indication that you are detecting 0 numbers of sources in these bottom flux bins. So the fact that this thing turned over was really, I think, a sort of unforgivable error. They should have at least stopped it for decency somewhere before it turned over. But it didn't matter. The damage was done, same damage. And as I said, Eddington bias was part of that damage. But confusion was the real damage. Now, here is an observation which jumps ahead in time to me observing with the Parkes dish in about 1974, yes, 1974. What this scan looks like is just a bunch of noise with a few sources detected. This is a twin beam system, a twin beam differencing system, so that you see positive sources and negative sources as you scan the twin beams across the sky and subtract the signal from those two twin beams. So there's obviously something real there, but most of it looks like noise, doesn't it? Well, let's see if that's true, because I did the scan, I did the integration again. This is about 30 minutes worth of integration. Here's the second lot. And you can see that, that every feature is duplicated. So what we're looking at here is what is known as confusion. And this is when you have a finite beam. In this case, it's an 8-minute of arc telescope beam. When you have a finite beam and a semi-infinite background of faint sources, and that beam simply integrates that faint background into a whole heap of lumps and bumps. That whole heap of lumps and bumps is known as the confusion limit. And so what we have here is, this is a double sky integration to the confusion limit. And just a few points. As I mentioned, it's a dual beam differencing system, so you get plus and minus. You should only believe sources. This is something that radio astronomers learned very painfully. You should only believe sources at a level of about 30 sources per beam area. 30 beam areas per source. So that is to say, there should be, on average, 30 beam areas for every source that you detect. Even then, you will still get some effects of confusion. Some sources will overlap. So out of this lot, maybe the 4 largest deflections are real sources. But the rest of this, and these, even these persuasive-looking spikes here and here, they're garbage. They're garbage in the sense that they are the background. They may be composed of several radio sources. The other thing to note from this picture is if you just randomly sample this confusion-limited scan, you get a highly non-Gaussian distribution of deflections. So that when you hear people talk about the confusion limit is 2 millijanskis, for example, they don't know what they're talking about, because we usually discuss things in terms of sigmas, but the confusion limit, if you work out what the confusion limit is for any steep source count, the answer is infinite, because there are sources in the sky of virtually infinite flux density. So confusion is highly non-Gaussian, and to describe it in terms of a Gaussian distribution is a bad idea. So next, I need to introduce my third protagonist, and this is Fred Hoyle, yet another radar pioneer. And here's an irony. Hoyle developed the Lloyd's mirror technique for measuring the height of incoming aircraft by the interference of waves coming directly, bouncing back directly from the aircraft and bouncing off the water to the receiver. So this is this was Hoyle's major contribution to radar, and this system has been used by navies forever. The other really best-known feature of Hoyle, certainly to most people, was the fact that he was a fantastic radio presenter and publicist. He wrote, I think good is perhaps a little strong, he wrote passable science fiction, The Black Cloud, for instance, A for Andromeda. But he was a truly brilliant theorist, physicist, cosmologist. He worked out how galaxies could get angular momentum from tidal torques. He was instrumental and crucial to the famous B squared FH, 1957, Burbage and Fowler and Hoyle. This is how stars make the heavy elements, for which, curiously enough, Fowler got the Nobel Prize. None of the other three got anything. He's perhaps best known in cosmology for cosmologists and astronomers anyway, as the major proponent of the steady-state theory in 1948. Curiously enough, Bondi and Gold wrote one paper, and he wrote the second paper. They didn't publish the discovery of the steady state as a triumvirate. Primordial helium abundance, and then subsequently, and I'll come to this, he went off onto some pretty interesting ideas of where we came from, and he was also a strong proponent of non-cosmological redshifts. And from the original steady state, he developed with Narlicker and Burbage, he developed a thing called the quasi-steady state universe, which he claimed explained everything that we see, and at the same time meant that everybody was rushing like a herd of buffaloes to the standard cosmological model, which we generally accept. And I guess there was a place for this, but I don't know of anybody who's read that book from start to finish. He won, of course, all kinds of honors. And then these two guys, Hoyle and Ryle, whom I got to know pretty well, what did they have in common? Well, pretty well everything, you would think. They were radar developers. They're both left-wing socialists. Both accepted knighthoods, nevertheless. And when Ryle's knighthood was in the offing, he went round and apologized to every member of his group for accepting the knighthood for the good of the Mullard Radio Astronomy Observatory. Both anti-war. Ryle was an active CND person. They both had brilliant, lightning-fast, lateral-thinking minds. You didn't have to spend more than 5 minutes with each of them to realize this. They were environmental activists before the days of global warming. They each founded an institute, essentially, at Cambridge. So you would think these people would be able to get along, wouldn't you? What happened? They fought at every opportunity. Every opportunity. They had totally different research leadership philosophies. Ryle built his institute with his group, sort of ingrown group or inbred group, although that's not a particularly flattering term to use, but he ended up with a group who would run through fire for him and who really admired and carried out his every wish, and they were an extremely talented group of instrumentalists and astronomers, no doubt about that. Hoyle had the completely different philosophy, but his institute, the Institute of Astronomy, was put together by getting a big chunk of money to attract visitors from everywhere. So they were totally different research leadership style, in research leadership style. And Ryle said to me once, I don't accept this idea of somebody giving somebody a big pot of money to have their friends come and work with them. But anyway, it's a long and painful story. But 1948, they had their first public argument. This was over the nature of solar radio bursts. They were both dead wrong. It was Shklovsky and co-workers in Russia who worked out plasma oscillations. In 1951, they began fighting about radio catalogs. Ryle claimed that radio stars were local. They were galactic. They were isotropically distributed because they were so damn close. Hoyle claimed that this was jumping to conclusions. There was no evidence one way or the other. And at the same meeting, Gold ventured that they might be some kind of strange galaxies like Seyferts. And apparently the attack on Gold went on for some 30 minutes. In 1955, they began fighting properly. And as Woody Sullivan says in his wonderful book, Cosmic Noise, this is history of early radio astronomy, and I recommend it thoroughly. It's fascinating. But in his words, Ryle and Hoyle again went after each other like a mongoose and cobra. And now, of course, Hoyle really had something to get his teeth into. So after 2C, what did really happen? Well, Cambridge very rapidly realized the error of their ways. And Scheuer invented this marvelous P of D technique to which I've already alluded, in which you simply look at the deflections and plot the distribution of deflections rather than counting individual sources. And Scheuer worked out how, with an interferometric system, you could, from that plot of deflections, the probability of deflection D, you could work out what the true source count actually was. And Hewish joined in this and worked with Scheuer, and from which they deduced that the true slope is minus 1.7. This paper of Scheuer's is one of the most elegant that I have ever read, and just for its elegance alone, it's worth reading. So the true slope, the true integral slope, Cambridge rapidly realized, should be about minus 1.7. But the damage really had been done, and the credibility lost. And Hoyle just leapt on this and claimed for years. And to me, personally, he said in 1969 when I met him, and I said, well, what did truly go wrong? He said, I just do not believe that they ever understood their data, and they still don't. Well, I don't think that was correct. They did understand it fairly quickly. Finding this as minus 1.7 instead of minus 2.7 caused, it is rumored, enormous ructions within that tight-knit group of the Cavendish, of the Mullard Radio Astronomy Observatory at the Cavendish. And in fact, Scheuer did disappear to Australia for 2 or 3 years, not long after that, but he came back. Then Mills in 1957 was involved in a survey. He had invented the Mills cross, a technique of making a pencil beam with a large, synthesize a pencil beam with a large cross antenna. And he began his survey, and the first thing he did, of course, was the bit that he could reach in the north to overlap 2C to see what the hell the fuss was about with 2C. And he found that about 60% or 80% of the 2C sources were non-existent. And this is, as I was saying, because they were simply confusion bumps and not real sources. Mills thought that measured the true slope of about minus 1.8. This is the Mills-Slee-Hill survey. The true integral slope was about minus 1.8. Or he said maybe it's about minus 1.65. I'm not quite sure where that came from. But anyway, the real blow-up came in Paris in 1958 when Mills presented his results and Ryle backtracked on his results, and they argued and argued, and it was clear to everybody that radio astronomy, extragalactic radio astronomy, was in severe disarray. This is just another picture of a simulated P of D in one dimension this time. And you can, and from this simulation, we found in which we popped sources on the sky according to an integral count of minus 1.5. When you actually count these bumps, you find a slope of minus 2.2. So this is what the confusion limit does to you. Gives you a whole bunch of apparently good-looking sources way above the noise, but they're as individual sources, they're garbage because the beam has integrated several sources into one. So, disaster for extragalactic radio astronomy, because not even the radio astronomers now agreed, and Hoyle had a field day. Hoyle and Ryle had very different public persona. Ryle hated public speaking, was a very nervous and shy public speaker for reasons that none of us can understand. Hoyle, on the other hand, had a marvelous, blunt Yorkshire delivery, slow and deliberate, and you just knew when you heard the words coming out of Hoyle's mouth that they were the truth. He really was such a convincing speaker. So this, of course, didn't help the issue. The whole discovery of this of the slope being steeper than minus 1.5 was really lost in these arguments about confusion limit and about interpretation. So what happened subsequent to that? Well, quite a lot of things. Quasars were discovered in the 1960 to 1965 era. 3C273 in 1963 was found to have the astonishing redshift of 0.16, which, when we look back on it now, never really ceases to amaze, because Minkowski had already found a galaxy with a redshift of 0.46. So why a redshift of 0.16 should bowl people over was not at all clear in hindsight. But the additional sky surveys at Cambridge and at Parkes found that this initial slope was indeed minus 1.7, minus 1.8, which everybody said, oh, that's okay, that's close enough to minus 1.5, no problem. Hoyle, Burbage, and Arp then got hold of non-cosmological redshifts. They did not believe that this 0.16 represented anything on the Hubble scale. And to be fair, there was excellent physical justification for this idea that these redshifts, the quasar redshifts, were wrong and did not indicate distance. Because if these objects were as compact as radio astronomers would have them believe, and if they were stellar in appearance, they should blow themselves apart in seconds by the Compton catastrophe. So there was, that of course assumed uniform radiation field, and this problem was essentially solved by Martin Rees in 1967, 1968, when he discussed non-isotropic emission. And it was solved even more when VLBI radio astronomy showed that the compact areas of quasars were in fact highly directed jets, relativistic speeds, so that the luminosities you were measuring in particular the luminosity of the jet coming towards you bore absolutely no real relation to the true luminosity, the total luminosity of the object. Then in 1965, Penzias and Wilson discovered the cosmic microwave background, and the hot Big Bang universe was instantly in play. At that point, everybody said, who cares about source counts? It doesn't matter. These radio astronomers can't really agree, and the slope's near enough to minus 1.5, so who cares? The hot Big Bang universe was almost immediately accepted, but not, of course, by Hoyle, Burbage, Arp, and co-workers. Well, finally, somebody came along and did a decent pencil beam survey at a high frequency. The idea of surveying at a frequency, extraordinarily high frequency of 2.7 gigahertz, seems ludicrous these days, doesn't it? But the idea of surveying the sky at these frequencies was my supervisor's John Bolton, one of the founding fathers of radio astronomy, and the discoverer with Stanley of the first discrete radio sources. Mind you, the positions that he found for those first discrete radio sources were not even in the right constellation, but that's yet another story. We did this sky survey with a system I've already mentioned. The receiver group at Sydney built a receiver at 2.7 gigahertz, which was a differencing receiver on the Parkes telescope. It had twin beams, 8 minutes of arc, and separated by about 20 minutes of arc on the sky. Our survey never went down to anything like 30 beam areas per source, so we're way away from the confusion limit. And by the time it got finished, up in 1976 or 78, when I'd long left the scene, virtually all the southern sky, with the exception of the equator, had been done, and in fact, these northern areas up to plus 25 degrees had also been covered. So this at last was a decent pencil beam survey, simple statistics that everybody could understand, way away from the confusion limit. And what did we find? Well, first of all, we found what John Bolton had predicted, that when you went to a higher frequency, you found a whole bunch of radio sources with strange spectra instead of the steep spectrum objects which you found in the low frequency surveys of Ryle et al. You found that 40% of the objects had so-called flat radio spectra. The spectra either tipped up as frequency increased, or in fact was completely inverted. This is indicative of synchrotron self-absorption. The compact features that I was describing a moment ago, the relativistically beamed features, and most of these objects we were immediately able to identify on the Palomar sky surveys, which reached way down to 19th or 20th magnitude. Most of them were identified with blue stellar objects, and subsequently were confirmed as quasars, quasi-stellar objects. What we found was a source count of almost exactly minus 1.5. So I was the first person in history to find a source count of minus 1.5. That's a minor claim to fame. I'll come to how useless that claim was in just a moment. What we found was that the counts were markedly flatter than the low-frequency Cambridge survey results. We now believe the Cambridge survey; they got it right. This is the Cambridge source count, or a line representing the Cambridge source count, and you see that our counts were significantly flatter. As I said, minus 1.5 versus minus 1.7 or minus 1.8. We now know why that is. It's because the different populations sampled, but that's another story. I met Hoyle about this time, in 1969, and of course, and the reason I met him was because Hoyle and Bolton were great friends. So my supervisor, John Bolton, was and his wife Letty were marvelous entertainers, and had most visiting astronomers that came through Parkes ended up at wine-soaked dinners at the Boltons, and so I got to meet Hoyle that way, and I also had an 8-hour car drive with him at one point, which helped quite a lot in discussing various issues. So anyway, we published these results in Nature to virtually no response at all. Because source counts at that time were pretty well dead and buried. Then what happened is, once a significant amount of this survey was done, I nipped away to Canberra because I had to spend the last year of my thesis work at Canberra. I was doing a degree with the Australian National University. So I had to go. My degree was with the Australian National University Mount Stromlo Observatory, jointly with CSIRO Parkes. So my supervisor was John Bolton, but yet I had to have a Stromlo supervisor as well, and I had to spend the last year of my thesis work at Stromlo writing up. So I went off to do that, but just before I did that, this is an aside, a short intermission. I was called back from Canberra by John Bolton to bolster the team at Parkes, where the Parkes telescope, still my favorite dish, the Parkes telescope was used as prime station for the Apollo moonwalk, the first moonwalk, and it was our signal that went out to the billions watching. And here is Neil Armstrong landing on the moon. Here is we had everything in the control room to monitor the situation. Here is, you can't see it, but here is the chart recording of the heart rate of Neil Armstrong as he stepped on the moon. 112 beats per minute. I mean, sorry. The point I was going to make is how slow his heart rate was. I cannot imagine doing anything that exciting and having my heart rate at simply 112.
That looks like a confusion plot.
It does look more like a confusion plot, but don't worry, we were able to do the P of D analysis on it, and 112 was his heart rate. There has been, this is us in the control room watching all this happening. Here's John Bolton, Taffy Bowen, head of CSIRO, another radar pioneer. And this is me, I know, because of the sweater, which Carol Jackson said she knew it was me immediately because I was still wearing that sweater 30 years later, but that's malicious. But there was, ever since the movie The Dish came out, it has been my lot to be accused of being the nerdy student in that story who had some girlfriend troubles. But I've strongly refuted this image, both aspects actually. I've strongly refuted that ever since. But then another picture came to light, and I think it weakens my story substantially. Guess who? Guess who? I think it's those black-brimmed glasses that do the damage. Anyway, back to real life. Here was my first cosmological calculations. I wanted, at Stromlo, we'd done the first part of the survey. I wanted to really try to figure out what the source counts actually meant. And I got back to Stromlo, and they said, oh, by the way, you've got a new supervisor. I said, who's that? They said, Alan Sandage. I said, oh, okay, well, I can ask him about how to do these sums. And he said, you should do them in shells, like the M-log pi diagram, which astronomers in the old days used to build up the luminosity function of stars in our galaxy and to examine the distribution of stars in our galaxy. I don't imagine anybody in this room remembers those. Maybe Harvey does. Sorry, Harvey. Sorry. But anyway, so I put together the equivalent M-log pi diagram, which in my case consists of S for the flux for the magnitude and redshift. I put into that diagram all the redshifts that we knew, and this is it, actually. These were all the redshifts we had for radio sources in 1969. Just about 30 or 40. It seems unbelievable, but that's the way it was. So I put them into this diagram, and then I tried to mimic it with Friedman models, simple Friedman models, uniformly filled. And this is what I found. Here's the old scruffy, sorry, it's full of dust and stuff, the old Nature paper picture, which I showed you earlier. And that observed line here is the same as is the same as our solid dots, our really observed source count. And this is what I found. that when you did these sums properly for a simple Friedman universe, you got nothing like 1.5. You didn't even get a slope as steep as minus 1.3. And subsequent to that, the realization dawned on me that these guys who had argued, and argued almost to the point of violence about whether the slope was minus 1.5 or not, or whether it was greater than 1.5, were completely out to lunch. That unless the slope, the initial slope, was minus 1.3 or minus 1.2, you could not entertain the idea of a uniformly filled universe. This actually amazed me to realize that not Mills, not Bolton, not Burbage, not Hoyle, nobody had actually put these objects into a cosmological context whatsoever. Because to get the slope to minus 1.5, it's very true that if you extend this on down to infinite flux densities, you'll get a slope of minus 1.5 eventually. But then you'll be at the point of one source in the sky, or no sources in the sky, because you're right off the scale of flux measurement for radio sources. There just are none.
Just because these guys are rare.
No. In what sense? There's just not enough sky ever to see a source, or sources, or a pair of sources which would obey a slope of minus 1.5.
But if they have common things, then space is locally Euclidean.
Oh, yeah.
Minus 1.5.
Oh, I can find populations locally, which of course are minus 1.5, have a minus 1.5 slope. Yeah. So I concluded that no uniformly filled relativistic universe count remotely resembles the observed count. And that's true whether you did the source counts at 2.7 gigahertz or at 0.1 gigahertz, as Ryle and company did. Didn't matter. So I came back to Parkes with my thesis for John Bolton to have a final look at it. And I said, John, John was a firm believer in steady state because he was a friend of Fred's, and he said to me at one point, it's almost the only article of faith I really have is that I believe in a steady state universe. So I had this news to break to my supervisor that this didn't work. And I wasn't looking forward to that particularly, so I thought I'd front up and say it straight away. And he said, so I said, John, I've got to tell you about my source count sums. And he said, no, wait, I've got news to tell you first, really good news. And I said, what's that? He said, I've managed to persuade Fred Hoyle to be your thesis examiner. So anyway, I did get through that. In fact, Hoyle was very kind to me, really. What happened next? Well, I left Parkes. I spent the next sort of 3 or 4 years at Parkes working hard on 1970 to 1974 doing the survey. And then I went to the Cavendish Lab. And when I broke the news to John Bolton that I was going to take up a fellowship at the Cavendish, I expected again an explosion from him because John's relations with the Cavendish were like every other radio astronomer in the world with Cavendish, pretty poisonous. But John said, that's the best place you can go. He said, that will give you perspective. That's just the right, Cambridge is exactly the right place for you to be. So I was encouraged by that. He also said, you'll meet Ryle. I said, of course. And he said, actually, I have great respect for Martin Ryle. He said, not as an astronomer, but as an engineer. I think he's a great engineer. So anyway, I went off to Cavendish with these various preconceived ideas. And I got the sums done properly with Malcolm Longair and Tim Pearson, and presented the first results of these at 1976 IAU. And these were those first results. Here's the source count now in what we call the relative differential form, in which you just take the observed source counts and you divide them by what you expect in each. You take the observed differential source count and you divide the number in each flux bin by the number that you would expect in a Euclidean universe, which we know doesn't exist. So if 1.5 minus 1.5 had been the true answer, you would have a horizontal line in this picture. So here's what we found. If we tried to use a steady state or a uniformly filled universe of any kind, we got this kind of curve, and the normalization was fixed by the way we did this at this point. And chi-squared said there was 1 chance in 10 to the 960 of this actually fitting the data. But then if you abandoned that normalization and just shifted it up and down to get the best fit possible, you managed to arrive at this best fit of 1 chance in 10 to the 80, which we still think pretty well ruled it out. So we then did some work on evolutionary models. And it was at this IU 74 that I had an insight into Ryle. Of course, I met him immediately, as soon as I got to Cambridge. I was sitting in Malcolm Longaire's office, and this smiling face came round the door and said, "Hi, I'm Martin. Do you have a few minutes?" And I thought perhaps that I did have a few minutes to chat to him. So he turned out, we got on extremely well. He turned out, at least to me, to be one of the kindest men that I ever met. I couldn't reconcile this picture with the ferocious temper that I'd been led to expect and the mood swings, etc. To me, he was an absolute gentleman, and indeed he mended my car. The astronomer Royal actually fixed my broken car at one point. He said, "Where is your car?" I told him, "Oh, I've got a breakdown." "Where is it?" He said, "I love fixing cars." He went out and fixed it. Anyway, but then I'd never seen this really tense, upset side of Martin until IAU 74. And then Burbage got up and gave his usual thing about steady state being right and non-cosmological redshifts were the right way of looking at things. And Ryle stood up and repeated his argument of 1955 that if you had the objects that close, then it was no use. The sky would light up in radio waves and fry us all. So they had to be at a much greater distance than Burbage would have it. And Burbage just stood there and smiled. And at the end of this day, I remember going up to Martin, and he was just picking up some overheads or something, and I noticed he was absolutely shaking, completely shaking, and his face was white. I said, "Martin, what's wrong?" He said, I tell it the way it is, and they never believe it. They won't listen. They won't listen. I will never, ever go to another astronomy conference." He never did. So that was Martin. He felt things so intensely, and he just never could seem to realize that Burbage was an expert in taunting him, and that he could just take a step back and have some perspective and let it go. So what happened to these guys after 1974? Well, Ryle became ill about 1978, and he was secretive about that. We never really knew what he had, but it was pretty clearly lung cancer. But he had already drawn away from radio astronomy towards alternate sources of energy, and he was building strange-looking propellers in the radio astronomy workshop. He never went to a conference again, to my knowledge. Hoyle, of course, continued to pursue steady state with Burbage and Narliker. And in fact, when I was at the Royal Greenwich Observatory, they used to ask me every summer if they could come and spend a month or two together in a quiet room away from the Institute of Astronomy, where they could sit quietly and work out this quasi-steady state universe. And I unwittingly then contributed to this different approach to cosmology by being happy to provide such hospitality. You can look at this book if you wish, but I don't think you'll be edified. You can also read Hoyle's bibliography, Home is Where the Wind Blows. Some of that's true, but it does go to show that the worst people to describe their own lives are themselves. So my contention is what the great surprise discoveries of the 20th century actually were, is that this item should be included, that cosmic evolution of a population of galaxies, Ryle and Shore, 1955, was a great discovery, and it's been borne out as true. But of course, at the time, because of the fights between radio astronomers and because of the errors by Ryle and his group, it was lost. Modern radio source counts, of course, we have them at all frequencies, from sky surveys at all frequencies with all instruments. And I just wanted to show you that is the area that the original fights were all about, the original argument as to whether the slope was minus 1.5 or greater. So modern radio astronomy has taken us well past that. And I'm finished. Sorry, I'm overrunning, but I finished, except to say that evolution was not really accepted until 1980. Beatrice Tinsley and company began to talk about it for galaxies. And the Durham group, Tom Shanks and Richard Ellis and company, showed that blue galaxies, red galaxies were explainable in a uniformly filled universe. Blue galaxies were not. They definitely showed evolution. The Space Telescope, HST, has showed us that those blue galaxies are merging, interacting, faint proto-galaxies, essentially. We have evolution through the star formation rate now. The Lilly-Maddow diagram, and this is a modern compilation. This part is good in the sense that it's well established at low redshifts, but the more distant redshifts, the problems remain of trying to work out what the dust obscuration actually is for the star formation, what effect it has on the star formation rate, calculated basically from the UV. We have shown that evolution, which we now see for all kinds of quasars, actually more or less fits the evolution found by found for the star formation rate. And semi-analytic galaxy formation has now concluded that galaxy makers, that there is an actual use for AGN instead of them being some silly fireworks stage of interest only to specialists and plasma physicists and so forth. Because to affect cosmic downsizing, we need some way of stopping galaxies continuing to grow and get bluer and brighter forever. To make modern galaxies look like red small galaxies, you really need to stop the star formation. And one way of doing that is putting them through an AGN phase to blast the cool gas out of the galaxy. So a use for AGNs at last, and my conclusions are very weak. Personal sadness to see these two giants place themselves in such a situation. Why couldn't they play nice? Why couldn't they do, for example, the sort of collaboration that Penzias and Wilson and Dickey and Peebles et al. Did to work out what CMB meant, or what the excess radiation meant? It's incredible to think that Hoyle and Ryle were together at Cambridge, the world's best cosmologist and perhaps in the world's best observer, and they couldn't see to work out what their results actually meant. I've mentioned how Hoyle and Ryle were both seriously affected. I've mentioned that the course of cosmology and galaxy formation should have been altered, but it took years. These are pathetically weak conclusions, I think. It's important. Of course, we need competitiveness, but hanging on to some perspective, when I think of how Hoyle spent the remainder of his life. It really, it's a bit like Einstein's years of looking for grand unified theory, perhaps. But perspective is a pretty important thing. And perhaps, again, perhaps some results come ahead of their time. And this business of galaxy evolution was, in 1955, was a pretty novel and surprising concept. And perhaps the parallel is Zwicky discovering dark matter in 1933 or whenever, and it not being accepted until rotation curves of galaxies by Vera Rubin came out in the mid-1970s. So thank you.
Well, I've got to admit I've taken some personal lessons from your talk. Douglas, I think we should stop arguing and let's start collaborating. Go into science. Yes, Harvey.
Well, Jasper, thank you for picking me out as something I might remember something from 40 years ago. The thing about 273, my recollection of it was such a spectacular thing because it was a point source. And so it was different than, it was different from radio galaxies. It was a point source. And I think that's what all the excitement about that was. And one last just a comment, and I'd like to hear what you have to say about it. I met Burbage many times. In fact, because we had him here as a colloquial speaker 25 years ago or something, and I remember distinctly him, he smoked a cigar and he put it out on the carpet of Eddington Bias.
Sorry, who is this? I missed the name.
Burbage.
This is Burbage.
Oh, yeah.
He ground the cigar into the carpet. But, you know, I always had the impression listening to him that he never believed this stuff anyways. I mean, for him it was an intellectual exercise and a way to be different. And I don't think he believed this for a second when he was proposing. Was that your impression, or is that?
I was never quite sure of that point. But he was certainly much more interested in the intellectual exercise aspect than he was in what was actually true. Whereas Ryle always nailed his colors to the mast. I mean, even when radio stars were radio stars, you know, Ryle was apparently enormously upset to discover that they weren't when Cygnus A was identified by Bada and Minkowski. So yes, I think there's a lot in what you say. I think Burbage did regard much of this as an intellectual exercise. And again, it's so important, I feel, to emphasize that Burbage was a great physicist. He did lots of fantastic things. And the trouble is, likewise Hoyle did fantastic things. And the problem is, what we remember them for is these very controversial, well, let's face it, dead wrong views of the universe.
Can I want to offer a comment and then ask a technical question? The comment is why Penzias and Wilson got along so well with Dickey is they weren't astronomers and didn't come into this with an opinion that could be right or wrong, so they were perfectly happy. I mean, that's quite a difference than two groups which have a clear view, meaning.
But still, why couldn't those groups have enough perspective to listen?
No, all I'm saying is Penzias and Wilson are a good role model.
Yeah. Yes, I see what you mean, yes.
The technical question is, so you've convinced me, isn't it always better to do a PFD thing than ever count sources? So why, in the end, even in your wonderful pencil beam survey, did you bother counting? Didn't you have more data than that?
We were nowhere near the confusion limit. We were noise limited. So
So there was not much to be gained.
there was nothing to be gained except counting a lot of noise. I mean, we would simply have had a distribution with a few real sources in the tail, and then the noise distribution would constitute the bulk of the deflections.
So just to clarify, you really believe that Hoyle never even conceded that the Big Bang might be true? Is that what you
I don't think he ever did. I don't think he ever conceded that it might be true. I think he genuinely believed, and I think that the die was cast when he said they just don't understand their data. And then he stuck to that. And he believed from then on that they didn't understand their data for some unknown reason, while surveys were being done by other groups all over the world who had no vested interest in Ryle's thesis. So I genuinely believe Hoyle went off the rails there and just stuck to steady state as an article of faith almost.
Yeah, because in geology there have been similar sorts of disagreements about the continents drifting, and people got terribly emotional. And again, it's a situation where the data is all interpretation, right? It's a similar sort of emotional conflict that you've got.
Somewhat ironic. The name Big Bang Theory came from Hoyle as making fun of the theory in a BBC radio interview.
Yes, I forgot to mention that point. Thanks, Chair.
Yeah, you should put it on his contribution.
They'll first listen to the chair. You'll get. Remember, we're not going to argue anymore, Douglas. We're going to collaborate. It's going to be another Penzias and Wilson.
That's so disappointing.
Yeah. But let's start with
just a comment, Jasper, to how, as you say, to reinforce your statement that emotions were really running high. I heard from Brian Robinson once told me that he went to Cambridge as a young graduate student, late 1950s, I guess, and he wasn't even working in this area. He was working in the medium spectral lines. And he passed Ryle in the stairwell. And they hadn't even met, but Ryle knew that Brian Robinson was Australian. He took him by the lapels and just banged him up against the wall.
I have heard the same story from Brian Robinson himself. I don't believe it. I believe that Hoyle lost his temper at Brian Robinson. I don't believe any of the physical stuff. Ryle was just too gentle a man. Even Tony Hewish, who worked with him in the same office virtually for 40, 50 years, said there was no violence whatsoever about Ryle. And I really believe that. Brian did embellish stories. And I've heard two versions of it. The one Brian told me was that it wasn't the Australian results from Mills and Company which had upset Ryle. It was the fact that Brian had been operating some kind of radar sounding thing because he was in the ionospheric group. He was with Radcliffe's crowd. And he was operating some kind of radar system. And Ryle had come in from a very bad night of observing with a lot of interference, which had essentially wrecked his nights observing. And he believed that Brian Robinson's radar had done the damage, whereas it was at completely the wrong frequency. But Ryle was just livid about this. And Brian Robinson again told me that Ryle had taken him by the lapels and pushed him against the wall.
And speaking of embellishments and for dissenting opinion, Douglas was shouting out something.
I was just arguing with you, Jim.
Yes.
So now that I'm feeling old, Cambridge still hasn't gotten over this. So when I was there were people on one side of the road who were from Hoyle's Institute, even though Hoyle was long gone. And there were people on the other side of the road from Ryle's Institute, even though Ryle was dead by the time he was there. And it's still the case that people wouldn't cross the road or wouldn't listen to guys from the other side of the road because they were obviously idiots. And it's still the case. Now they have this brand new building and they're trying to get people from both places to go in. Some of the people are saying, "Over my dead body." What the hell are you?
Well, I didn't get that. When I was there, I was amazed to discover that when I went there, I was the first postdoc ever from outside the group. Every one of the other postdocs had come up through the group. So it was a very closed group. But I was made very welcome, and I think that crossing this road, I mean, a number of people did cross the road and go to each other's colloquia. I remember it distinctly. And I don't really remember, I do remember Ryle having feelings about the Institute of the kind that I've expressed. But I never got any feeling from the group itself that they had anything against the Institute to stop them going there. They would go there for a decent colloquium, but if it was this theoretical stuff, why bother to walk half a mile?
Coaching.
Well, my history of knowing Ryle goes way back. He was the first one I wrote a letter to as an undergraduate wanting to work with the Ryle group at that time. Unfortunately, just before the negotiations could be completed, Taffy Bowen from CSIRO came through India and offered a fellowship to go to CSIRO, which also didn't come through, and finally went to Harvard. So Ryle very encouragingly wrote a very nice letter to start the negotiations for a scholarship and all that. It was just Taffy Bowen talked me out of it.
That's interesting. My experience was somewhat similar. I was going to go to Cambridge. I was accepted by a college at Cambridge. You have to be accepted by both the college and by the Mullard. But I never heard from Mullard, and I kept prodding them, and they kept saying, "Oh, Martin Ryle's just about to write you a letter to invite you." But in the meantime, John Bolton came through University of Toronto, and before I knew it, I had an offer in writing within 2 weeks from the Australian National University to go to CSIRO. So that's what I did.
Yeah, so I ended up talking with you for probably many hours about measuring counts. I'm kind of amazed in retrospect. I didn't realize you were the first person to do this calculation of actually measuring, the volumes, taking into account the expansion of the universe. So did all these guys just go, no. I can't believe.
I didn't actually ever publish it, believe it or not.
So
I thought everybody else must have done this 100 times, and what am I missing? I was brand new to doing this kind of sum. I didn't know that I'd done it correctly. I thought it was okay for a thesis chapter.
So you just chatted to Sandage, and he's like, oh.
Sandage and Egan had another of their fights at that point, and Sandage had huffed off to the United States again. But that's another interesting story. I thought Sandage would grab onto this, and he had a bit of a reputation of grabbing problems from students, and I was a little bit nervous about this. So I told him about it. He just said, do it like M log pi, and that's the only advice he gave me and the only interaction we had. He wasn't interested in the sums, and I think he was a dyed-in-the-wool optical astronomer, frankly, with a typical view of wire welding radio astronomers.
And I just wanted to offer a comment here. It's pretty easy, I think, to just be puzzled at how stubborn these steady state guys were. And just because, anybody my age or younger, this whole stuff was the CMB was discovered when I was in elementary school or something, right? We all take for completely comfortable this remark that says we're not in a special place, and that you use that to make all kinds of inferences about the universe. And in the 50s, it was just as obvious that we wouldn't be in a special time. But, I can't defend these guys after 65 or 67 or something like that. But up through some time, it's just they're not being idiots to think that it's really, really kind of wrong to consider if the universe had a start, then we live in really quite a special time. The last moment, you couldn't tell it would last forever or something. That's really, it's as silly as saying that we live in the center of, the only galaxy or something. This doesn't cover the last 30 years of Hoyle's or Burbage's life or something like that, but it does cover when they were 40 and screaming at each other, some of it.
Yes, it does. And there were, of course, philosophical, not to say religious issues involved here as well. Certainly the philosophical issue of the universe not having a beginning was very attractive to a huge number of scientists.
Including Einstein.
Including Einstein.
Time for one more question or comment? Before we close with an ancient historical perspective from Dr. Richard. Right. Let's thank Jasper.